Hello, everyone. My name is Dr. Garrett Starkov, and today we'll be talking about chemical bonding. First, we'll start by talking about compounds and how they bond, some implications for engineering, some example problems, and then some practice problems for you to do on your own. The vast majority of matter that we encounter day to day is in the form of compounds. Compounds are assemblages of elements. We talked before about how elements are the very basic fundamental building blocks of matter, and compounds are when those elements are assembled together. One compound that you're familiar with is table salt. That's sodium chloride, NaCl. Sucrose, another compound that you're commonly familiar with. Table sugar is C12H22O11. So that tells us that the way that carbon, hydrogen, and oxygen bond in sucrose is a 12 to 22 to 11 ratio. Now think about the materials around you right now. Do you think you are being exposed to any elements right now? As I said before, the vast majority of matter that we encounter is in the form of compound. You can only think of one element that you might have been in contact with, like technically two, but one you might not know about. And that would be gold. If you have 24 karat gold jewelry, that is just gold. It's not bonded with anything else. It's gold held together with metallic bonds. But silver, most silver is actually only 95%. So there's other things in there too. So that would make it a compound. Even the air that you're breathing. So like I said, aside from jewelry, I don't think you're really encountering any elements right now, except the only one that you are encountering is argon, that I can think of at least. So even nitrogen. So the air that you're breathing, nitrogen is N2. It's actually a compound of two nitrogen atoms. Oxygen is a compound of two oxygen atoms. It's O2. Argon is a noble gas, and it's roughly 1% of the atmosphere that you're breathing right now. So yes, you are being exposed to one element all the time, but that's probably about the only one, at least at a level that you can observe or notice. The elements in compounds are held together by chemical bonds. One is metallic bonds. That's when you have electrons shared between metal ions. One is covalent bonds. Electron pairs are shared between atoms when the outer shell is either full or nearly empty, either nearly full or nearly empty. Examples are oxygen, nitrogen, that's C6H12. Sorry, that's glucose, blood sugar, and sulfate, SO4, 2 minus. It's very common in organic chemistry. That's why I use glucose as an example. Ionic bonds are actually bonds through electrostatic attraction that are shared between positively and negatively charged ions. That's really common in inorganic chemistry. So organic chemistry is often covalently bonded. Inorganic chemistry, generally ionically bonded. So as I said before, metallic bonds are formed between two metal atoms. The specifics are actually not really of concern for civil and environmental engineers. We don't really care how the metallic bonds are being formed. What we do care about is the bulk material properties. We want to know how dense it is, how strong it is, how stiff it is. So Young's modulus is a stiffness. For what it's worth, those come from metallic bonds. So we can figure out how dense, we can measure how dense something is. We can measure how strong something is. And that's actually just derived from the metallic bonds. When you destroy some steel, when you pull steel apart, it's actually being torn apart at the atomic level. So it really is a metallic bond that's holding it together, but we only really care how strong it is so we can build buildings out of it. Covalent bonds occur between nonmetals to form molecules. So you expect to see like CO2, for example, is a covalent bond between two nonmetals. Valence electrons are shared in order to acquire the electron octet shell of a noble gas, with two exceptions: hydrogen and boron are other than 8. So most things like to have 8 in their outer valence electrons. Hydrogen and boron are the two exceptions. We can use Lewis dot structures to determine the number of electrons available for sharing. So let's look at hydrogen, oxygen, carbon, and how they combine together to form diatomic oxygen that we breathe, water, CO2, and CH2O. So if you think about the Lewis dot structure, for hydrogen, it's really simple. It's just a one dot. So that is the Lewis dot structure for hydrogen. For oxygen, it's a little more complicated. Oxygen has 6 electrons in the outer shell. 1, 2, 3, 4, 5, 6. So it has 2 vacancies, basically. It wants to have 8, but it only has 6. So there's 2 places for things to bond to oxygen. Carbon has 4 electrons in the outer shell. And we can tell, by the way, looking at the periodic table, we can see that everything in that group, carbon, silicon, germanium, tin, generally have 4 electrons available in their outer shell because of the group that they're in. So we can look at these. So we have H, O, and C, hydrogen, oxygen, and carbon, and we can see how do they combine. So if we want to make oxygen, O2, oxygen is actually a double bond. So it's got, each one has the 4 electrons that are happy. They're kind of just doing their own thing, but it's missing 2. And so it actually, in a way, you can kind of think about it like one oxygen atom kind of like shares 2 electrons, and the other one holds on to them. But because they're sharing, because now if you look at their individual electron clouds, like if I look at just the cloud of this one, it has 8 electrons that I was trying to get. And if you look at the oxygen, not the oxygen, but the electron cloud of the other one, so I'll just erase this circle so you can see what I'm talking about. If you look at the electron cloud of the other oxygen, it also has 8 that it's experiencing. So it's stable now because it has 8 electrons. H2O is kind of similar. You start with oxygen. It's got 4 electrons that are not being shared, and then it happens to share 2 electrons with hydrogen. So now hydrogen is happy. It's got 2 electrons. That's what hydrogen likes to have. And then oxygen is happy because now it seems to itself that it has 8 electrons. CO2, remember carbon has 4. It has 4 electrons, which means it's missing 4. So it wants to hold on to 4 electrons from some other people. And oxygen is missing 2. So oxygen and carbon actually form double bonds again in CO2. And then for CH2O, again, we start with our carbon. It's got something like this with the hydrogens and the oxygen. It still likes to hold 2 electrons from oxygen and 2 electrons, or 1 electron from the hydrogen. And if you look at the individual shells, well, I forgot to draw in the rest of the oxygens. So if you look at the individual atoms, every one of them has the number of electrons it likes to have. Oh, you know what? I drew too many. Whoops. Just go back. See, even professors can make mistakes. So now everyone has the number of electrons they'd like to have. So you look at oxygen, it's got 2, 4, 6, 8. 2, 4, 6, 8. Carbon has 1, 2, 3, 4, 5, 6, 7, 8. Excellent. Over here on this one, oxygen also has 8. Carbon has 8. Everyone's happy. All right, and there will be one of your practice problems will be to draw a Lewis dot structure. So keep that in mind. Keep this slide in mind, I should say. The way we name covalent bonds, or covalently bonded material, I should say, the most metallic nonmetal is listed first. It's the one farthest left on the periodic table. Like nitrogen is farther left than oxygen, so it's NO2, not O2N. Carbon is farther left than oxygen, so it's carbon monoxide, not OC, oxygen carbide. And then hydrogen is farther left than oxygen, so it's H2O. We use prefixes to indicate the number of atoms, such as mono, di, tri, tetra. You can read those if you want. Carbon monoxide versus carbon dioxide. That tells us that it's CO versus CO2. So CO2 would be carbon monoxide is this. Carbon dioxide is that. So that di just implies there's 2. So what is dihydrogen monoxide? Well, it's H2O. Dihydrogen, 2 hydrogens, 1 oxygen, monoxide. And then also that ide, so IDE gets added to the end of the second molecule. So carbon dioxide, it's not carbon dioxygen, it's carbon dioxide. Switching gears, we were talking about covalent bonding for a while there, but now ionic bonding is when you have a bond between a metal cation and a non-metal anion. Previously, I mentioned that covalent bonds occur between 2 nonmetals. Ionic bonds occur between a metal and a nonmetal, with a large difference in charge. And a large difference, like +1 may not seem like that big of a difference, but it is. So sodium and chloride, sodium has a +1 charge, chloride has a -1 charge, so you get sodium chloride that forms. And that's an ionic bond. Ions are atoms or molecules with a positive or negative charge. So anything that's charged could be called an ion. Cations are positively charged, anions are negatively charged. I remember which one's which by looking at this. So a T kind of looks like a plus sign, so positively charged. and an N is in negative. So an anion is negatively charged, a cation, the T kind of looks like a plus sign. So that's how you can remember those two. The ions above might actually be covalently bonded molecules. So something like sulfate, SO4 here, is a covalently bonded, it's two nonmetals that have covalently bonded together, but because it has a -2 charge on it, it can actually bond with other things. So you can get sodium sulfate, hydrogen sulfate. Hydrogen sulfate actually is sulfuric acid. So H2SO4, two hydrogens because you have a +1 charge on hydrogen, one sulfur because there's a -2 charge on sulfate. Same thing with phosphate, and then even there's a couple, only one that I can think of off the top of my head that's actually a cation. So ammonium is a cation that has a +1 charge. So you can actually get ammonium sulfate probably, Na4 2SO4. So you could, I think, have ammonium sulfate form. Those are sometimes called molecular ions. I learned them as I always call them polyatomic ions, meaning that they're like ions. They're charged, but they're a molecule, not an atom. Compounds that have ionic bonds tend to dissolve easily in water, and they also tend to make the water electrically conductive. And that has to do with the polarity of water. Water itself is polar. Ionic compounds generally are kind of polar too. We'll talk about that in a second. Here's an example of some of your polyatomic ions, or molecular ions, if you want to call it that. It's a covalently bonded element with a charge. So we can use that to estimate how ionic bonding will occur. So for example, if we have hydroxide over here, you see hydroxide has a -1 charge. So if you're combining hydroxide with sodium, it would be sodium hydroxide, because sodium has a +1 charge, hydroxide has a -1 charge. If it were calcium, on the other hand, calcium has a +2 charge, so it would be calcium hydroxide is actually OH2, not CaOH. So it's CaOH2, calcium hydroxide. And I guess because it's not covalent, remember we talked about covalent ions, covalent compounds, you add that you add like the prefix. So you might think we would call this calcium dihydroxide, but generally speaking, it's not called that. It's just called calcium hydroxide. Oh, but let me go back. There's a lot of different polyatomic ions. I did my PhD research on perchlorate, which I think is right here. Yeah, so perchlorate is a oxidized form of chloride. There's a lot of other ones that are oxidized forms of chloride too. So you have ClO3, ClO2, and ClO4. And it's weird because they all have a -1 charge. And then even there's one more, this one, ClO, also has a minus charge. And you might recognize that term. Hypochlorite is bleach. So calcium or sodium hypochlorite is what you buy when you buy bleach from the store. Very, very reactive. It's a very active compound, so it breaks down the dyes in your clothes or kills germs. When electrons within a molecule are shared unevenly, that molecule becomes polar. Polar, much like north and south pole of a magnet or north and south pole of the Earth. So you have hydrogen has a positive charge and oxygen has a negative charge. And when they come together, because it's not a symmetrical bond, it's a bent bond, a bent structure. Because of that, you get a slight differential positive charge. So a slight differential positive charge on the hydrogen side and a slight differential negative charge on the oxygen side. And so because it's polar, it's able to dissolve things and kind of interact with things that are also polar. They like to have that slight charge difference. Something like methane, CH4, down here on the right, is nonpolar because it's totally symmetrical. The way that hydrogen bonds to carbon in this case is a symmetrical bond. Polar compounds tend to dissolve well. So most ionic compounds are somewhat polar because they're a plus and a minus, and they tend to share that unevenly. But then nonpolar compounds, so most covalent compounds are nonpolar. If you think about fats and greases, those are nonpolar compounds, and they're also they do not dissolve well. But this is a little bit far afield, but if you take a fat and you cleave off the fatty acid and make it and put a positive charge there, it actually becomes a soap. It actually becomes so polar, and because it's polar, it's able to dissolve in water. And so soap is made by taking fats and making them polar. What would be the chemical formula of a compound made from calcium and phosphate? Okay, so we can go back. Let me just scroll back actually a couple slides and look what phosphate is. So phosphate PO4 with a 3- charge. So calcium is a +2. We can tell that by looking at our periodic table. +2, it's in the second group. +2 charge. Phosphate is a negatively charged with a -3. That's supposed to be a 4, sorry. Never very good at writing on these screens. Calcium phosphate. And so the way it would combine is you need 3 calciums for every 2 phosphates. So it's going to be a 3-to-2 ratio. And we just write that like this. Calcium, 3. And if you think about that, now you have 6 positive charges and 6 negative charges. And so it cancels out, and they're able to bond together in that ratio. So the ratio is really important for this. And the way you could write the equation like this: calcium 2 plus so 3 calciums plus 2 phosphate is in equilibrium with calcium phosphate. What is the name and Lewis dot structure of a compound containing 1 carbon atom and 4 fluorine atoms? So fluorine is similar to chlorine. It's in the same group. It also has 1 electron that it wants to share. So fluoride has 7 electrons, and it wants to have 8. So it needs to share one of those. It needs to borrow an electron from someone else. Carbon, if you recall, has 4 electrons. That means it has vacancies for 4 more. And so you get 4 fluorines for every carbon. Now, if you remember, we talked about prefixes. Because there's 4 fluorines, it would be a tetra. So carbon tetrafluoride. CF, carbon tetrafluoride. Actually, don't worry about that. Carbon, as we said before, it has 4 electrons. Fluorine has 7. 1, 2, 3, 4, 5, 6, 7. And so fluorine would form something like this. Carbon tetrafluoride would look something like this, I mean. Now, all the fluorines have 8 electrons that are being shared. The carbon has 8 electrons being shared, and so it's a happy camper. And last but not least are some practice problems for you to work on your own. All right, I hope that was useful for you, and I know you'll be using stuff like this in your future classes. So thanks for your attention.